Chapter 3.0 Triangle Review. Starting with naming angles and sides. Angles are named using capital letters. An angle could have just one capital letter to represent it, or a series of 3 capital letters to indicate which angle is being represented. When an angle is named with a series of 3 letters, the angle we are looking at is the middle letter. Angle A, which is here, can be written as the angle symbol and then capital A, or it can be written as angle BAC, which means start at B, go up to A, and then go to C, and the angle that's formed between those 2 lines, which would be here, is the angle we're looking for. Or we could name it angle CAB, which means go from C to A and then to B, and the angle formed between those 2 lines, which would be here, is the angle we're interested in. Angle B can be written as, we could call it angle B if we're using 1 letter. If we're using 3 letters, we can start at angle A, go to angle B, and then go to angle C. So from A to B to C, the angle in between those 2 lines is angle B. So that would be angle ABC, or we could start from C, go to B, and then go to A, still talking about the same angle. So we can name it angle CBA. And then angle C, we could just use 1 letter, angle C. If we're using 3 letters, we can start from A, go to C, and then go to B. Angle formed is angle C, so we can call it angle ACB. Or we could start at B, go to C, and then go to A, still talking about angle C here. So we can also call it BCA. Sides of a triangle can be named several ways. A side can be denoted by a lowercase letter or a pair of capital letters that represent the angles at which the sides start at. In this triangle, the side opposite from angle A is here, the side opposite it would be here. We can call that little a, or we can call it line segment BC, capital BC, with the line on top means line segment, or we can call it line segment CB because the capital letters on either side are B and C. So the side opposite from angle B, which would be here, can be written as lowercase b, or the angles that are on each end of this side are A and C. So we can call side B line segment AC or line segment CA. And the side opposite from angle C, which would be here, can be called little c, or the 2 angles at either end of that are A and B, so we can call it line segment AB or line segment BA. Labeling sides of this is more specific to right triangles. Always label the hypotenuse of a right triangle first. The hypotenuse is the longest side, and it is found opposite the right angle. So from the right angle, we go to the side opposite. That would be our hypotenuse. Adjacent means beside, so it's the side that is touching the angle you are referring to. And opposite is the side across from the angle you're referring to. So in a right triangle, we obviously have a right angle. Across from that angle is the hypotenuse. Then we're going to have another angle that we are referencing. In this particular diagram, that angle is here, the bottom left angle. Then the side across from that angle is the opposite side, and the side that is touching that angle but is not the hypotenuse is the adjacent side. Notice that the adjacent side and the hypotenuse form the angle. Okay, that can be called the angle of interest. Label the following triangles with respect to the angle indicated. My angle is in the bottom right. I'm starting with the hypotenuse. So from the right angle, go across. The side that is across from the right angle is the hypotenuse. Then from my angle of interest, go across to the side opposite it. That is the opposite side because it's opposite the angle. And then the other side, it is touching the angle but not the hypotenuse. That is our adjacent side. Next one, label our hypotenuse. It's across from the right angle. Our angle of interest is here. The side across from that angle is the opposite side. And the third side, the side that is touching the angle of interest but is not the hypotenuse, is the adjacent side. Pythagorean theorem. The Pythagorean theorem can be used to find a missing side length when you have a right angle triangle and you know the other two lengths. Because not all triangles are labeled A, B, and C, and sometimes side C is not the hypotenuse, we can use the formula side squared plus side squared equals the hypotenuse squared, or leg squared plus leg squared equals the hypotenuse squared. On your formula sheet, it might be a squared plus b squared equals c squared. Just know that whatever the sides are called, c has to be the hypotenuse. Let's do this for this triangle. Label the hypotenuse. In this case, that is the side that we are trying to find, which means our other two sides go in for A and B, or for side and side, or for leg and leg. Then we get 3 squared plus 4 squared equals the hypotenuse squared. 3 squared is 9 plus 4 squared is 16 equals the hypotenuse squared. 9 plus 16 is 25, which equals the hypotenuse squared. Now we want the hypotenuse, not the hypotenuse squared, so we're going to take the square root of both sides, and we would get square root of 25 is 5 equals the hypotenuse. So the hypotenuse equals 5. This is editing Corey here. I don't know what the heck was going on when I wrote hypotenuse. That's not hypotenuse. It's not what that says there. So, should be hypotenuse. My brain and hand were clearly not coordinating at that point in time. So it should be hypotenuse, which is this. When I go back to the rest of the notes, it will be wrong like it was before. Note, remember that if you are given the hypotenuse, you will need to subtract to find the missing side. Example, determine the missing side length to the nearest tenth in the given triangles. First one, 8, 5, and x. Which side is our hypotenuse? It is opposite from the right angle. So that's the side we're trying to solve for. Then we have side squared plus side squared equals hypotenuse squared. Plug in our information. That gives us 5 squared plus 8 squared equals x squared. 5 squared, 5 times 5 is 25. 8 squared, 8 times 8 is 64, equals x squared. 25 plus 64 is 89, equals x squared. Then we want to take the square root of both sides to get x. Need my calculator for that one. Square root of 89 is 9.4339. And we'll round to the nearest tenth, as it says up here. So that would give us x equals 9.4. Next one, we have 6 and 10 and y. Which side is the hypotenuse? It's across from the right angle. So it's the side with measurement of 10, which means we're solving for one of the other sides. So in our formula, side squared plus side squared equals hypotenuse squared. We have one of the sides is 6 squared, plus the other side is called y squared equals the hypotenuse, which is 10 squared. 6 squared, 6 times 6 is 36, plus y squared equals 10 squared, 10 times 10 is 100. Now we need to subtract because we need to isolate the y value, so subtract 36 from both sides. We get 0 there. Y squared equals 100 minus 36 is 64. And then we don't want y squared, we just want y. So square root both sides to get y equals the square root of 64 is 8. So y equals 8. (3.1) and 3.2 trigonometric ratios. Note, when doing trig questions for Math 10C, you must remember to change your calculator to degree mode. For TIs, you push mode, then go down until you're at degrees radians. Move over till you're on degrees and hit enter. For Casios, you do shift, menu. For Casios, from your calculating screen, do shift, menu, go down to angle and push F1 for degree. So I can show you the TI version. I can show you the TI version with my calculator. You would go mode, down to radians, degrees, move over, so I'm highlighting degrees, hit enter, and then just exit. To check if your calculator is in degree mode, you can push the sine button and then 90. Sine 90, it should equal 1. If it equals 1, you're in degree mode. If it doesn't equal 1, you're in radian mode. So change it to degrees. So our trig ratios are sine theta. This symbol is called theta. It's a Greek letter. Just means an unknown number, and we usually use it for angles. So sine theta equals opposite over hypotenuse. That's the opposite side divided by the hypotenuse side. So in this triangle, our opposite from the angle of interest is here. Our hypotenuse is here. And our adjacent side is here. Then cos theta, the full name is cosine theta, equals the adjacent side divided by the hypotenuse side. And tan theta, the full name is tangent theta, equals the opposite side divided by the adjacent side. You can only use these for right triangles, and we have a method of remembering what each of them is, which is SOHCAHTOA. SOHCAHTOA. So sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and TOA, tan, is opposite over adjacent. Example, write each trigonometric ratio: sine A, cos A, tan A, sine B, cos B, and tan B. So starting with sine A, cos A, tan A, that's saying looking from angle A. If we make angle A our angle of interest, label your sides opposite, adjacent, and hypotenuse. This should really have a right angle there. That's supposed to be a right angle. So label our sides based on angle A. So our hypotenuse in a right triangle, it's not going to change. It's based on the right angle, which would be here. But our opposite and adjacent depend on which angle we're looking from. So from angle A, 12 is opposite. So I'm going to put opposite A, and 5 is adjacent. So I'm going to put adjacent A. Then I want to do sine A, cos A, and tan A. I can write SOHCAHTOA to help me remember which one is which. First one, sine. So, S-O-H, sine is opposite over hypotenuse. Sine of the angle, which in this case is A, equals the opposite side. From angle A, opposite side is 12. Divided by the hypotenuse, which is 13. Then sine A equals the fraction 12 over 13. Next is cos of angle A. Cos is adjacent over hypotenuse. The adjacent from angle A is 5, and the hypotenuse is 13. So 5 over 13. Then tan of angle A, tan TOA, tan is opposite over adjacent. Opposite from angle A is 12, and adjacent from angle A is 5. So 12 over 5. Now we want to repeat that process, but we want to look from angle B. Angle B is over here. Our hypotenuse will be the same because that's based on where the right angle is. So that's still 13. Opposite from angle B is this side over here. So this is opposite B, and adjacent from angle B is the 12 side. Adjacent. Then do our trig functions. First one, sine of B. Sine is opposite over hypotenuse. The opposite from angle B is 5, and the hypotenuse is still 13. So 5 over 13. Cos of angle B. Cos is adjacent over hypotenuse. Adjacent from angle B is 12. Hypotenuse is still 13. So 12 over 13. And last one, tan of angle B. Tan is opposite over adjacent. Opposite from angle B is 5, and adjacent from angle B is 12. So 5 over 12. Then we've written each of the three trig functions for both angle A and angle B of this triangle. Example, write each trig ratio sine theta cos theta. Example, write each trig ratio sine theta cos theta tan theta. So theta is this angle here at the top. Label our hypotenuse first from the right angle. It's the side 20. Then from theta, label the opposite side, which would be 16, and the adjacent side, which would be 12. We can write it our SOHCAHTOA again. SOHCAHTOA. The trig ratios are also on your formula sheet, so you can just look at your formula sheet to see which side goes on top and which on bottom for each of the ratios. Sine is opposite over hypotenuse. Opposite from angle theta is 16, and our hypotenuse is 20. Then sine theta is 16 over 20. Cos theta. Cos is adjacent over hypotenuse. Adjacent from theta is 12, and hypotenuse is 20, so 12 over 20. And then tan theta. Tan is opposite over adjacent. Opposite from theta is 16, and adjacent from theta is 12, so 16 over 12. Notice that for sine and cos, we have a number less than 1. 12 over 13, 5 over 13, 5 over 13, 12 over 13, 5 over 13, 5 over 13, 12 over 13, 16 over 20, and 12 over 20. That happens because sine and cos both have the hypotenuse as the bottom number, and by definition, the hypotenuse is always the longest side in a right triangle. So sine and cos, so the ratios for sine and cosine have to be smaller than 1. The bigger number has to be on the bottom. Tan could have the larger number on top, or it could have the larger number on bottom because it's just opposite over adjacent. So we could have an example where we've got a bigger number on top, so that fraction would be greater than 1, or the bigger number could be on bottom, so that fraction is less than 1. But tan is the only trig ratio that could be bigger than or equal to 1. Cos and sine have to be smaller than 1. The ratios for cos and sine have to be smaller than 1. Evaluate each trigonometric ratio to 4 decimal places using a calculator. Get into the habit of using brackets. First one, sine of 60 degrees. What it means by get into the habit of using brackets is when you put this in your calculator, put sine and then 60 in brackets. So we're in degree mode. We have to be in degree mode for this to work correctly. Then we do sine. My calculator already gives me brackets, so if yours does too, great. If not, just put open bracket, then 60, and then close the bracket, hit enter, and it says to 4 decimal places that we want the answer, so equals 0.8660. The number after that fourth digit is a 2, so that would not round up. Next one is cos 45, so push the cos button, then brackets if you need them, 45 inside the brackets, enter, we get 0.7071. And then tan 30, push the tan button. Then if you need brackets, put brackets and 30 inside the brackets, and we get 0.577. There's a 3, but then followed by a 5, so the 3 would round up to a 4. And remember on the last page, we said that the sine and cosine ratios always have to equal a number that is smaller than 1. And notice this is smaller than 1, this is smaller than 1. Our tan number happens to be smaller than 1. It could be smaller than 1, it could be bigger than 1. But sine and cos, they have to equal a number smaller than 1. Finding an angle. Whenever you have an angle as your unknown, you must press the second function button or the shift for Casio to get your answer. Example, what is the measure of each angle to the nearest degree? So we have that sine of the angle theta is equal to 0.4384. That means sine, remember, is opposite over hypotenuse. So the opposite side divided by the hypotenuse side equals 0.4384. We want to calculate the angle. So we want to move the sine over so that theta is left by itself. We're trying to separate the sine function from this unknown theta, just like if we have 3x and we're solving for x, we would divide by 3, because division is the inverse function for multiplication. The inverse or opposite function of sine is called sine inverse. Very creative, I know. So we do theta equals, we do sine inverse to both sides. Sine to right inverse, we do -1, so sine inverse on that side, and sine inverse on this side. And remember, opposite operations undo each other. So sine inverse and sine cancel each other out. We're left with theta on the left equals sine inverse 0.4384. To do sine inverse in your calculator, you do the second function button or the shift button on a Casio, then you push sine, and then you type in your number, 0.4384. Calculate, 26.001. We'll round to the nearest whole number, the nearest degree. So theta equals 26 degrees. Next one, cos theta equals 0.2079. Again, we want to move the cos part to the other side of the equal sign. So we have to do the opposite operation, which is cos inverse. Do that on both sides. Cos inverse and cos cancel each other out on the left. We're left with theta equals cos inverse of 0.2079. Then in our calculators, second or shift, then cos. If there's not brackets already, put brackets. 0.2079, enter, and we get 78.0006, ... So theta equals 78 degrees. Tan theta equals 1.4281. Same idea, we want to move the tan part to the other side of the equal sign. So do tan inverse on both sides. Tan inverse and tan cancel each other out. We're left with theta equals tan inverse of 1.4281. Notice that tan is equal to a number greater than 1, and that can only happen for tan, not sine, and not cos. Then we calculate tan inverse, so second or shift, and then the tan button, Then inside the brackets, put 1.4281, enter, and we get 54.999, which rounds to 55 degrees. So theta is 55 degrees. Example, draw a triangle to represent tan theta equals 5/4. Calculate the measure of angle theta to the nearest degree. From our formula sheet or from SOHCAHTOA, we get that tan theta equals the opposite side over the adjacent side. In this question, that's equal to 5/4. So the opposite side is 5, the adjacent side is 4. Draw a right triangle. Doesn't super matter what it looks like as long as it's a right triangle. Pick an angle that's not your right angle to be your theta. It could be this one down here, or you could have chosen it to be this one up here, one of those two. From the angle that you choose, label the opposite and adjacent side. This side here would be opposite, which is 5 in this question. So that is 5, that's the opposite side. And then label the adjacent side, which would be down here. And the adjacent side is 4. And then it says to calculate the measure of angle theta to the nearest degree. So we have that tan theta equals 5/4. This is the same as the questions above, except instead of having a decimal number, we have a fraction. We're going to do tan inverse of both sides to move the tan over. Tan inverse and tan cancel each other out, so we get theta equals tan inverse brackets 5/4. And then we calculate second tan brackets if you don't have them, fraction 5/4. If you don't have a fraction button, just put 5/4 inside the brackets. And we get 51.34, which would be theta equals 51 degrees to the nearest whole number. Example, draw a triangle to represent sine theta equals 6/14. Calculate the measure of angle theta to the nearest degree. From our formula sheet, sine theta equals opposite over hypotenuse. In this example, it's equal to 6/14. So our opposite side is 6 and our hypotenuse side is 14. Draw a right triangle. We know that our hypotenuse is more than double one of our sides, so I'll try to draw it to match that. Doesn't really matter if it's to scale though. My right angle, across from my right angle is the hypotenuse, which is 14. And then the smaller side is 6, and that is the opposite from our angle, which means my angle would have to be up here with the way I've drawn this, because opposite from that would be down here. And then we want to calculate angle theta. We have sine theta equals 6/14. We want to do the inverse sine to both sides to move the sine function over. Then we get sine inverse and sine cancel each other out, and theta equals sine inverse of brackets 6/14, close brackets. Then we calculate second function sine, brackets if you don't already have them, fraction 6/14, which is 25.37 or 25 degrees. Theta equals 25 degrees. Draw a triangle to represent cos theta equals 45 over 70. Calculate the measure of angle theta to the nearest degree. From our formula sheet, we have cos theta equals adjacent over hypotenuse. In this question, that is 45 over 70. So our hypotenuse is quite a bit bigger than our one side, than our adjacent side. So I'll try to draw that to sort of look that way. Hypotenuse side is across from the right angle. That would be 70. The side that looks like it's significantly smaller than 70 is here. So that would mean that has to be my adjacent side, which means I would have to put my angle here so that that is the adjacent side from angle theta. Then I want to solve for the angle. I have cos theta equals 45 over 70. We want to move the cos theta over, so do the inverse to each side, cos inverse. Cos inverse and cos cancel each other out. We get theta equals cos inverse brackets 45 over 70. Calculate that. Second cos brackets 45. This time I'll just divide. You can use the fraction if you have it. If you can't, then you enter it this way. 45 divided 70 inside the brackets. Calculate that. 49.99, which would round to theta equals 50 degrees. That brings us to the end of Chapter 3, Lesson 1.